So today I want to talk about the power gain definitions of an amplifier. Of course, what we want to do with an RF amplifier is we want to gain the power, or to amplify the power of a given source and give this to a certain load. So of course the power gain definitions are strongly related to the possibility how to measure it in the region of RF engineering. So what we have here is, first we have a signal generator, and I assume I have a certain amplifier and a power meter. So in the first step what we can do is that we connect the generator, our signal generator G, to our power meter. And here it's very important to discuss what will be the equivalent circuit of this. So normally if I sketch the equivalent circuit, I will have here a signal source, and this signal source will have a certain characteristic impedance, ZC, and in the most cases this characteristic impedance of a RF signal source is 50 ohm. So they are normally constructed for a certain system of characteristic impedances, and this is in most cases in RF engineering 50 ohm system. So also the power meter itself will have an input resistance of the same characteristic impedance. This means now we have here a 50 ohm characteristic impedance and here a 50 ohm characteristic impedance. That means now the power meter is matched to our signal generator, and this means we will not get an arbitrary power, but we will get what we call PAV, which is the maximum available power, because we have a matching now between our power meter and our signal generator. In the second step, we will connect our generator to our amplifier, and then the amplifier to our power meter. And if I set up now the equivalent circuit, it will look almost like this, that we have our signal generator again, which has a certain characteristic impedance ZC. But if I assume I have now an arbitrary amplifier, then this arbitrary amplifier will have a certain input impedance Zin, which will be not always identical to ZC. And here, if I have a look to the output also, I can sketch it like this, that we have here a certain output impedance Zout, which also will not be per definition equivalent to the characteristic impedance of our power meter. So I will not discuss now the source here. So here this is the equivalent circuit of our amplifier. And so we will not have any matching at the input in an arbitrary situation, and we will not have a matching at the output. So here we will assume that there is a certain power L which is given to the load. PL, this is the power to the load. So what we see here is in the first step we get the maximum available power, and in the second step we see that normally if I did not do any special consideration for the amplifier, we will not have a matching at the input and we will not have a matching in the output, so there will come a certain power, of course, to the load. And what we define now is the so-called transducer power gain, which will be defined as PL over PAV. So this is the transducer power gain, which we will discuss in further detail in the next step. So here I have again written the transducer power gain, and here I did a little mistake here. This must be written GT, not GTU. So the transducer power gain, GT, is the power into the load divided by the available power. Now I want to deduce an expression for the available power if I have the combination of the generator and the power meter. So in principle this here is our generator, G, and this is in principle the input of our power meter, PM. And in contrast to the preceding section, I assume that now our power meter would have a certain reflection coefficient, Rg, which is in principle a little bit more general than in the preceding section. But to get the available power, we then must determine or use a power meter which will have Rg conjugate complex. To calculate now the available power, we can just take, this is of course 1/2 B2 absolute value square. This would be the power which enters the power meter minus 1/2 A2 absolute value square, which describes the power which leaves the power meter. So we will have, this is 1/2 absolute value of B2 minus absolute value of A2. This will be the power, but at the moment we can also say that according to this relation we have A2 is Rg times B2, so we get for the available power is 1/2 B2 absolute value square minus, here you have to insert the absolute value of Rg absolute value square times B2 again, where we see that the available power will be 1/2 1 minus absolute value square of Rg times the absolute value square of B2. So our problem is now to relate the wave amplitude B2 to the original wave amplitude A naught. So you see here, of course, this consists of A1. We can say that B2 is equal to A1, but A1 you see is given by A naught plus RG times 1 times RG conjugate complex times B2, which can be written like this. So this is, I'll write it here, A naught plus RG conjugate complex times B2, which can be solved for B2 and here it must just be B2. So we have B2 times 1 minus absolute value of RG will be equal to A naught. And so we will find that B2 will be A naught divided by 1 minus RG absolute value square. Of course, you see here we have to insert B2 absolute value square. So here will occur the square and this will cancel against this. So we will get for the available power, it's 1/2 A naught absolute value square divided by 1 minus RG absolute value square. So now I want to discuss the power which will enter the load. Of course, we can again say that the power here into the load, I have here the wave amplitude BL which enters the load, and then AL which is reflected back by the load. So we will get, this is 1/2 BL absolute value square minus 1/2 AL absolute value square. But again, you see here that RL is RG times BL, so this is 1/2, I can write it like this, 1 minus RL absolute value square times BL absolute value square. So now we are in principle ready to define the transducer power gain, GT, and we have the power in the load which will be 1/2 1 minus RL absolute value square times BL absolute value square divided by, now we had of course here 1/2 A naught absolute value square divided by 1 minus RG absolute value square. Of course the 1/2 will cancel and we will get for the transducer power gain, it will be equal to 1 minus RG absolute value square times BL over A naught absolute value square times 1 minus RL absolute value square. So this will be the expression, with the help of this expression, we can calculate the transducer power gain. What we must know is in principle now BL and of course the ratio between BL and B naught, so as long as we know these two values. So this will be the next step. So I now want to discuss a special case that we use a so-called unilateral transistor as an active device. This means this unilateral transistor has no internal feedback, and also this means it's absolutely stable. So what we see here is the red elements. They are from our unilateral transistor, and then we combine in principle here. This is our signal generator, and this is our power meter. And if we want to calculate now what is the transducer power gain, then we know the transducer power gain is a function of BL over A naught. So what we have to do is in principle to deduce an expression of BL independent of A naught, of the wave amplitude generated by our generator. So in the first step we see, for example, that BL would be equal to B2, but you see B2 consists of two terms. One term is S21 times A1 plus a second term, and the second term is just plus here S22 times RL times BL. So we can solve this for BL, and we will find that BL is equal to S21 times A1 divided by 1 minus S22 times RL. Of course here we have to use A1. On the other hand, we see, for example, that the wave amplitude A1 is given by, of course, A naught here plus RG times 1 times B1, but times S11 times A1 again. So we find for A1 this is equal to 1 over 1 minus S11 times RG times A naught. So this is a function of A naught, and we of course can insert this here, and we will find for the BL, I write it like this, BL will be, so perhaps I start first with this term. This is 1 over 1 minus S11 times RG times now this term S21 times now 1 over 1 minus S22 times RL times now A naught. So what we have here is, perhaps I'll write it here again, BL is 1 over 1 minus S11 times RG times S21 times 1 over 1 minus S22 times RL times A naught. So what we have here is now the wave amplitude inside the load, independent of our wave amplitude, which is generated by our signal generator, and in between the generator and our load we have as an active device an arbitrary transistor, which is described by its exponent, and this we can insert into this equation. Now I want to go on and studying the so-called transducer power gain in the case of a unilateral transistor, which in principle is an ideal transistor. In reality, a unilateral transistor does not exist, but it's a very interesting ideal case. So we found for the transducer power gain this expression, and here we had to calculate BL over A naught. And in the case of a unilateral transistor, we get this expression for BL over A naught. Of course, now you see what we have to do is, in principle, we have to take the absolute value square of it and insert it here. And so we will get GT will be 1 minus RG absolute value square divided by the first term, 1 minus S1, 1 times RG, now here absolute value square, and of course then times S21 absolute value square times, and now you have here 1 minus RL absolute value square divided by 1 minus S1 S22 times RL absolute value square. And of course A naught square will cancel against this A naught here. So if we assume this ideal case of a unilateral transistor, then we have no internal feedback. S11 is S12 is equal to 0. And the nice thing is then that the overall transducer power gain subdivides in 3 terms. We can in principle right now GT is GG times S21 absolute value there times GL, and we define now GG is equal to 1 minus RG absolute value square divided by 1 minus S11 times RG absolute value square, and this we call the generator gain. And of course then we have here, well, sometimes this is also called G naught, is absolute value of S12. This is in principle the gain of our active device. And we can further on define the gain of the load, which is 1 minus RL absolute value square divided by 1 minus S1 S22 times RL absolute value square, and this is called the load gain. Of course, if we want to optimize now the overall transducer power gain for a certain transistor, of course, then S21 and S22 and S11, they are fixed. So what we can do is to optimize the so-called generator gain and to optimize the load gain, and this we will do in the next step. So what are deduced up to now was a transducer power gain in the case of a unilateral transistor. In case of the unilateral transistor, we get for the transducer power gain an expression which consists of three terms: the generator gain, the gain of the active device, and the load gain. So if I if I assume that I have a certain transistor in a point of operation, S21, S11 and S22 are given. So the only possibility is to maximize, for example, the generator gain is to use the reflection coefficient, or G, which the transistor sees. So we can write here, I will not do this in detail, but the maximum we get for, and if you go do the consideration, then you will find that you have to choose Rg equal to the conjugate complex of S21. And in this case, the generator gain reduces to 1 over 1 minus S11 absolute value squared. And also here, for this, we can find the maximum of the load gain again. The only thing, if I assume a transistor at a certain point of operation as S22 is fixed. The only what we can change is the load reflection coefficient. And also here we find the maximum for RL must be chosen equal to S22 conjugate complex, and for the generator load gain we then get this is 1 over 1 minus S22 absolute value squared. So that we now, if we maximize the generator gain and then maximize the load gain, we come to the so-called GTU, which is just given by 1 divided by 1 minus S11 absolute value squared times S21 absolute value squared times S1 over 1 minus S22 absolute value squared. And this is called the unilateral transducer gain. You see, the unilateral transducer gain does only depend on the scattering parameters of our active device or of our transistor. So it is like this, that for a real transistor I can always assume that S12 is 0, and then I can in principle at least calculate the unilateral transducer gain, which would be possible with this transistor. Of course, this gives you an idea of the overall gain which is possible, but the problem is that for a real transistor S21 is never 0. Nevertheless, I will discuss in the next step what, from a practical point of view, this optimization means. I here sketched the principal setup of an RF amplifier, which corresponds to our consideration in the section before. So we have here our active device, which is described by its S parameters, and we saw if we want to have the maximum power gain, or in our case we assume a unilateral transistor, that in our case we assume S12 is equal to 0. So then we saw that we can get the maximum power gain if we see here into this section of the circuit as one conjugate complex. And how can we realize this? This we can realize if I have a lossless input matching network, and we saw, for example, in the first section in our transmission line theory with the help of the Smith chart how we can realize a lossless input matching network. So the transistor itself must see here as 1,2 conjugate complex, but this corresponds to the point that S11 of the transistor is transformed here, so that the input impedance I see into this network must be equal or ZC. So S11 of our transistor must be transformed with the help of the lossless input network into the matching point ZC. The same holds true in principle for the output. Here we have to see S22 conjugate complex, and this again corresponds to the case that if I have to look, or if I look for the output impedance, then this must be also equal to ZC. That means also S22 must be transformed into the matching point. And if we assume now that, or of course we assume that our transistor is a unilateral device, then we get for the overall transducer power gain, the so-called unilateral transducer power gain, which is 1 minus 1 absolute value squared times S21 absolute value squared times 1 over S22 absolute value squared. So this will be, in case of a unilateral transistor, the power gain you can in maximum reach with help of this setup for the amplifier. So now I want to discuss the so-called bilateral transistor. In the case of the bilateral transistor, we have the internal feedback which exists. Of course, the ideal case will never exist, so always we will have a certain parameter S12. That means we have an internal feedback from the output to the input. And if you go through all the theory, then you find for the transducer power gain this expression. In principle, we know already this term and we know already this term, and these two terms are also known, but now we get an additional term due to the internal feedback. The output will, the reflection coefficient of the output will change the reflection coefficient I see into the input of this device, and vice versa, though also the generator reflection coefficient I see here, the generator reflection coefficient will have an influence on the S22 or on the output reflection coefficient I see into this network. And if you go through all this theory, then you can now also try to find the matching point. This means you want to do an optimum input and output matching at the same time, and you will see that this input and output matching is only possible if the transistor itself is stable. Otherwise, you cannot find a simultaneous input and output matching. So in the next step I will give the results. If we do an input and output matching, what will be the gain I can get from a certain transistor. I now want just to give the result for the so-called maximum available power gain. As I already pointed out, an optimum input and output matching is only possible for k greater than 1, and if you have a transistor which is stable, then you can do the simultaneous input and output matching, and then you will end up in the so-called maximum available gain, power gain, which is given by this expression here. But as we saw before, if I have a transistor which is not stable, you see in principle as soon as K becomes smaller than 1, then this expression is not meaningful anymore, because a power gain can only be a real number. So to get a crude approximation, what is available by a transistor which is unstable, we can say, or we saw that we somehow always can stabilize our transistor. This means we can somehow always find or change the value or change the circuit so that K is equal to 1 is reached, and then we get the so-called maximum stable gain, and normally this is written GMST. And to get the maximum stable gain, we just assume that we somehow realize K equal to 1. So if K is equal to 1, this term will disappear, and we can get S21 over S12 absolute value squared. So this will be the maximum you can reach, but of course this is a crude approximation, since we just assume that we somehow realized K to be equal to 1, and then we end up in this expression which gives you the maximum stable gain. Sorry, here just a G must be written, so this is the maximum stable gain here with the G. So we have the maximum available gain and the maximum stable gain here.